Okay, we're back to elementary calculus. In this video, I'm going to finish up section 4.4, which is just a couple of applications of integrals. So let's get started with the first one. The area between graphs. Okay, area between two curves. Done. Alright, so we have a couple functions. Y equals f of x and y equals g of x. And between two x values, say a and b, we're assuming, for the purpose of this picture, we're assuming that f of x is greater than or equal to g of x on this interval. So for x between a and b, f of x has larger values than g of x. Okay, so what we're after is between a and b, we want to know what is the area between these two curves. Like this. Well, essentially the basic idea is if we just wanted the total area if these are positive functions, so let's just assume that for now. If these are positive functions, if we wanted the area beneath the curve of f, that would be the total area from here down to the x-axis. That would just be the integral of f of x between a and b. If we wanted the area under g of x between a and b, that would be the the integral of g of x between a and b. So that would give us this stuff down here. So from this picture, the area under f of x consists of two parts, this part and this plus this part. So if I want just the area between the two curves, I would want the total area under f, and I'd want to subtract the area under g. So therefore, I have to erase the picture now. The area between, well, I can keep the picture for the moment and write it down here. The area between the two curves, so if I erase this shading, the shaded area now would be the integral of f of x dx from a to b. That would be the total area underneath f. I need to subtract the integral of g of x dx from a to b. That would be the unshaded part. So if I subtract, that leaves me with just the part in the middle. Okay, so let's do an example of this. Find the area between two graphs. Y equals 4x plus 1 and y equals 5x plus 3 on the interval 1 to 4. So this is an x interval here. Okay, so I'm trying to find the area between two curves, between two functions. So that means I'm going to integrate one function minus the other function. And the interval is going to be 1 to 4. So I'm integrating from 1 to 4. Now I need to figure out, though, which function goes here and which function goes here. Now let's assume, I mean, it's true for this example. We'll do more example in a second, but let's assume that we know already that these two functions don't intersect anywhere in this interval. So they're not the same on this interval. So that means one is definitely bigger than the other on this entire interval. So I need to figure out which one is bigger. So let's just plug in a number from the middle here, say 2. If I plug in x equals 2 to this function, I get 2 times 4 is 8, plus 1 is 9. If I plug it in here, I get 2 times 5 is 10, plus 3 is 13. So this is the bigger function on this interval. So that means I would integrate it here, 5x plus 3, and then put the smaller function here, 4x plus 1. So you have to figure out which of the two functions is bigger. That tells you which direction, which subtraction to perform. All right. So then the next thing is, these are two separate integrals, but they have the same bounds. And if they have the same bounds, I can combine them by subtraction in this case. I can go ahead and simplify by subtracting this function minus this function. And I can turn this into a single integral. So I have 5x minus 4x is x, plus 3 minus 1 is plus 2. So now I'm really just integrating x plus 2, which is just a single function, so it's going to be a lot shorter to do it this way. All right, so then let's do that. So we take the antiderivative of x plus 2. That would be 1/2 x squared plus the antiderivative of 2 would be 2x. And then we're plugging in 4 and 1. So evaluate at 4 and 1. That'll give us 1/2 4 squared plus 2 times 4 minus, so the entire function with 4 plugged in, minus the entire function with 1 plugged in. Okay. In the interest of space and time, if you simplify this, you should get 27 over 2. Yeah. So that's our answer. The area between these two lines, because these are lines in this example, the area between these two curves is 27 over 2. All right, let's do one more example of this type, but make it slightly more involved. I want to find the area, and I want to phrase it as this way: bounded by the graphs, so by the curves, let's say y equals 3x plus 2 and y equals x squared plus 2. Okay, so that's the entire problem. That's the way it's worded. So we're talking about the area between two graphs. These are my two graphs, but notice this time I'm not told what are the x values. Excuse me. I'm not told what are the x values that I'm looking at. And so that's where this word bounded comes in. Bounded means, let's think about what these two graphs look like. I'm not going to graph them precisely just yet. Y equals x squared plus 2, that's a parabola. It's a quadratic function, so it's a parabola. Since it's positive x squared, it's a parabola that's opening upward like that. Let me draw that. Draw very darkly there. Maybe my marker is running low. So y equals x squared plus 2 looks something like this. Y equals 3x plus 2. That's a straight line. It's sloping upward. So maybe it'll look something like this. Oh, that's much better. So it'll cut through the parabola somewhere. Bounded means there'll be some region that is separated off from the rest of the plane by these two curves. There's a region that's trapped between these two curves. Okay, so there are other parts that are between the two curves, like up here, but that's not a bounded region. That's an infinite region that's extending off forever. Same with over here, between the two curves back here, there's an unbounded region off in this direction. But there's one bounded region, which means it's cut off in every direction, and that's the area I'm after. Okay, so keep in mind what it is we're looking for. We're looking for the area of some region that looks like this. And so what I need to do is I need to find the x coordinates where the two curves intersect, because those intersection points will tell me where is my bounded region. It'll be between those two x values. Okay, so I need to find intersection points. So what I need to do is, the first step is find the x values where the functions are equal. Okay, so what that means is I need to take my two functions, 3x plus 2 and x squared plus 2, and I set them equal to each other. So 3x plus 2 equals x squared plus 2. Now I have an equation that I need to solve for x. So my first step would be, let's subtract 2 from both sides. I get 3x equals x squared. I guess the safest way to solve this is it's a polynomial equation, so let's get everything to the same side. Let's subtract 3x. 0 equals x squared minus 3x. Then we factor that. We can pull out an x from both terms. So x times x minus 3. And so my two solutions to that equation are x equals 0 from this factor and x equals 3 from this factor. So my result from this first step is x equals 0 and x equals 3. Those are the two x values where my two functions are equal. Those are the two x values where the curves cross each other, where they intersect. Okay, so with that in mind, let me erase. Now the question becomes, find the area between these two curves on this interval. So this is new information that we figured out now. The area between these two curves on the interval 0, 3. So now it'll be just like the previous example. I need to integrate one function from 0 to 3, and then subtract the integral of the other function from 0 to 3. Come on, back for more. The cat's back. Now we already know what the picture should look like, so we can figure out that the line should be bigger than the quadratic on this interval. But just like before, we can check that. If I plug in an x value from this interval, like 1, if I plug it in here, I get 3 plus 2 is 5. If I plug it in here, 1 squared plus 2 is 3. This is the bigger function. 3x plus 2 is the bigger function. So in the first integral, I'd put 3x plus 2. In the second integral, I'd put x squared plus 2. Okay, so we want to do this pair of integrals. Again, it won't help quite as much as the last one, but since it's the same, it's always the same bounds on these area between two curve problems, we can combine this and make a single integral. We'll have 3x plus 2 minus plus 2. The 2's will cancel. I'll have minus x squared and that'll be my simplified integral to calculate. Let me give myself some more space this time. So I want to integrate this. So let's erase this extra stuff. I'm just going to recopy it and then have the rest of the board to work. Alright, so antiderivative of 3x would be 3 over 2 x squared minus the antiderivative of x squared is 1/3 x cubed. Should use round parentheses there to avoid confusing it with the evaluation symbol. Get out of the way. 0 to 3. Alright, so plugging in 3, we get 3 over 2 times 3 squared minus 1/3 times 3 cubed minus, now if I plug in 0, I'll write it down, but in this case, for this specific function, when I plug in 0 here, 0 squared is 0, 0 cubed is 0, this is all going to be 0. So my answer is going to be whatever I get from just this part. So that'll be 3 squared is 9, so 27 over 2. 3 cubed is 27, divided by 3 is 9. So 27 over 2 minus 9. That will be 9's 18 over 2, so that'll be 9 over 2. Yeah. So our area between these two curves is 9 over 2. The area bounded by these two curves is 9 over 2. All right, so that's area between two curves. The first of our two applications in this section. The next one is called average value of a function. The average value of a function f of x on some interval. All right. So let's do it like this. This is on an interval a, b. All right. So some justification first, or motivation first. If I want to, this is. Let me hold off on telling you what the answer is, how you do this. Let's talk about what does it mean to take the average value of just a list of numbers. So this is an example first. The average of, let's say, 3, 4, 8, 8, and 10. So if I have these five numbers, if I want to take their average, there's basically two steps. First, I add up all the numbers. So 3 plus 4 plus 8 plus 8 plus 10. If I add those numbers up, I get a total for everything. But then I want to take that total and redistribute it so each of the 5 things has the same amount. So I take the total and I divide by how many pieces there were. So in this case, there were 5 numbers in my list, so I divide by 5. And so, not that it matters, but we do this. 3 plus 4 plus 8 plus 8 plus 10 divided by 5, you get 6.6. Okay, so that's a discrete problem, meaning that problem does not require calculus. It's just a discrete problem where you have a handful of numbers, you add them up and you divide by a number. What we want to do is extend this same idea to a continuous situation where I no longer have a discrete list of numbers. I have a function that's taking different values over this entire interval a to b. All right, so the picture is I've got some function from a to b. This is y equals f of x. And I want to basically figure out the total amount of y values I have. Now that doesn't really make sense because I have a y value for every single x value from a to b, and that's infinitely many. Okay, so I can't just add up the y values. But the analogous concept to that addition is the area underneath this curve. So if I want the so-called total for this function, the total value accumulated over this interval, that's just the integral. That's the area under the curve, or really the net area under the curve. So this total would be the integral from a to b of f of x. That gives me the area. But that calculation is the equivalent of the addition part of taking the average of the list of numbers. Then what I need to do is divide by basically all the x values, the number of x values. But again, that's infinite, so it doesn't really make sense to do it, to think of it exactly like that. The equivalent thing here is the length of interval. How far is it from a to b? And that's just b minus a. B minus a is the distance from here to here on the x-axis. So, the length of a to b, the length of the interval is b minus a. I don't know why I wrote that, but let me erase. It's worth saying, but it's not really that important to leave it there. So when we do the average value, I want to keep my picture because I want to do more to it. The average value I'm going to call f sub AVE for average would be, well, think of the two parts of taking average. First, you want to take a total. That's this integral. And then you want to divide by something. In the discrete version, we just divide by the number of numbers, the number of things in our list. In the continuous version, we divide by the length of the x interval. So we divide by b minus a. Okay, so it comes out to be 1 divided by b minus a. That's just going to be a number. So this problem is just going to end up being you integrate the function and then you divide by this number, or you multiply by this fraction here. Okay, it doesn't really make the difficulty any more. Okay, so the meaning of this is we're basically want to figure out if I were to take this region and take that area of the region and redistribute it so it gave me a perfect rectangle, how tall would the rectangle need to be? So what would need to happen would be I'd need to cut off some of this area from up here and then use it to fill in the dips in my region. So I don't know exactly where it'd be here, but maybe like this. Hopefully that is visible. So if I slice off this piece and this little piece, those areas, if I drew it properly, would fill in this extra piece and this extra piece, so that the total area would be the same. Okay, so the y value of that resulting rectangle would be f average, the average value of f. Okay, so you're just like we did in the discrete case, we think of it as we have the total amount, the total area, and we are redistributing it across all the x values so that you have the same y value at every x value. You're redistributing the area so it's all evenly distributed. Okay, so let's do a couple examples of this. All right, so find the average value of the function f of x equals x cubed minus 2x plus 5 on the interval 1 to 3. Alright, so all I have to do for this to find the average value is I just set up the integral of this function, x cubed minus 2x plus 5 dx. My interval 1 to 3, that tells me what numbers to put on the integral sign. Those are my two x values. And now this integral would give me the total. I had to remember to divide by the appropriate thing. And that's just, I do 1 over, and then it's just the difference in my x values. 3 minus 1. So in this case, that's 1/2. And now I need to integrate this. So the antiderivative would be 1/4 x to the 4th minus 2 times 1/2 x squared would give me just x squared plus 5 times x. And I plug in 3 and 1 and subtract. Okay, so let's plug in 3. And then I need to plug in 1. Let me be careful here. I don't want to. So I have to make sure that this 1/2 is applied to everything. So let's just do a big set of parentheses here. And have 1/2 outside of everything. Wait. Okay, so keeping track of my parentheses. Let's do brackets for this. So there is my function with 3 plugged in. Now I subtract my function with 1 plugged in. So 1/4, 1 to the 4th, minus 1 squared, plus 5 times 1. Alright, so let's just do this in the calculator. I'm gonna do these and then remember to at the end to multiply by 1/2 or divide by 2. So all of the integral comes out to be 22. Then I multiply by 1/2 and get 11. So the average value that this function takes on this interval is 11. Okay, so let's do one more example where it's a little bit more concrete type of function. So a real world example just to illustrate this a little bit clearer. So this will, if the picture explanation didn't make as much sense, then maybe this will be an easier way to think of it. So suppose I'm driving the car and my speed or velocity function is v of t equals 8t squared miles per hour. at t hours. Then I want to find the average speed between over the first 3 hours. So that's t equals 0 until t equals 3. Okay, now I could directly set this up according to the definition, but let me go through the steps of what it means, what the formula means, just to give you an alternate explanation for where it comes from. Okay, so like we talked about at some point, average speed would be the total distance traveled divided by the time it took to travel there. So you'd want distance divided by time. I don't have distance, I have speed or velocity. So my total distance like we talked about in the introduction to definite integrals, the total distance would be a number of miles. So to get that from speed, I would need to integrate this. I want to integrate my velocity function, 8t squared dt. I'm traveling from t equals 0 to t equals 3, so I'd integrate from 0 to 3. Okay, so we'll carry out that integration in a second, but that once I get that integral, that would give me a total distance. I want average speed, so I need to figure out what is my total time. Well, I'm going from t equals 0 to t equals 3, so that's 3 minus 0 hours. So this would give me miles here on the integral. My total time would be 3 minus 0 hours. So that's 3. So my average speed would be my total distance divided by my total time. That's this divided by 3, or 1/3 integral from 0 to 3 of 8t squared dt. And now miles divided by hours would give me miles per hour again. Right? So this is exactly the average value formula. There's my integral, there's 1 divided by my length of the input interval, 3 minus 0. Alright, so that's figured out now. I'm going to recopy that. So V average, my average velocity would be the answer to this problem, dt. So antiderivative of 8t squared would be 8 over 3 t cubed, oops, from 0 to 3. And plugging in 3, that would give us, let's combine these coefficients. So I can multiply the 1/3 times the 8/3. That gives me 8 over 9, 3 cubed, minus 8 over 9, 0 cubed. 0 cubed 0, so it's just this. 3 cubed is 27, divided by 9 is 3. So that just gives us 3 times 8 is 24. And so this would be our miles per hour. Over the first 3 hours traveling it with this velocity function, our average speed would be 24. Right. So this concludes the material for homework 11. I'm going to stop the video since I don't want to start a new chapter with just 5 or 10 minutes left. So the next video I start will be over section 4.5, which is the beginning of homework 12, and can't remember if I said this specifically, but what I want to do, so like I said, there are a couple sections that I initially planned on covering in the course that aren't necessarily essential. One of those sections is 4.7, which is part of homework 12. It would just be too rough to try to show you on a whiteboard without having access to like a second viewing screen at the same time, and it's not really that important of a section anyway. So I'm going to skip 4.7. So on homework 12, it will the only parts that matter for the homework are going to be 4.5 and 4.6. So specifically, problems 15 through 19 on homework 12, you can just ignore. I won't count them against you on your grade. I'll work it out when I'm figuring out homework grades. But that means we have two sections, 4.5 and 4.6, to cover for homework 12. That'll probably be my next two videos. It should just take about one video a piece, but we'll see. Alright, so I'll stop this video here.